Thank you. All right. Good afternoon, everyone. Had lunch? Yeah. Okay. So, are any of you those who missed the first session today? Can you have a show of hands? 1, 2, 3. Anybody else? Okay. So I'll do a quick summary since at least I did not do it for you, I guess. Right. So yeah. So what we'll prove is we will prove Tutt's theorem, hopefully, which says that a graph has a perfect matching. Matchable means a graph has a perfect matching. If and only if, whenever you delete a set of vertices, let's say you delete k vertices, the number of components in the resulting graph that have an odd number of vertices, we call them odd components, that should be less than or equal to k for every subset of the vertex. What is not too difficult to see is that if you have a set that violates this condition, then the graph definitely does not have a perfect matching. So that is the easy direction which we have already observed, and if you missed the session, you might want to make a drawing and figure it out. What we will focus on is proving the difficult direction, which is that whenever this condition holds, for every set, graph actually has a perfect matching. Contrapositive, if the graph doesn't have a perfect matching, then there is a precise reason for it, which is some set that violates this condition. There exists one such set, at least. Yeah. And before we get into Tutt's theorem proof, let us first discuss some cool consequences, which, as we discussed earlier today, actually have their roots in the four-color conjecture historically. Right. So what we will prove is that every two connected three-regular graph, three regular means every vertex is degree 3. Two connected means the graph is connected. If you delete any vertex, the resulting graph is still connected. Every such graph has a perfect matching. And we will prove a stronger statement, which is that every such graph actually has a stronger property, which is that every edge belongs to some perfect matching. So not only is there a perfect matching, there is a perfect matching containing your favorite edge for every edge. Okay. So that is what we will do. Yeah. Questions, concerns? Is that okay? Did you attend the morning session? No. Okay, then you can talk to your neighbor, who can probably summarize it for you. Okay. Alright, so basically whatever I have written here is things we wrote here earlier today. Yeah? So I'll erase this part. So let's try to prove the first consequence, Petersen's theorem. Right. So we have a two connected three regular graph, and our goal is to show that it has a perfect matching. What we would like to do is we would like to conclude that G has a perfect matching, QED. Let's fill this up. Yeah. All right. What do you think we should do? Should you show that there is a perfect matching, or should you, given the statement, what would you try? Maybe I'll erase this. Is this what you would try? You have a two connected three regular graph. You want to show that there is a perfect matching. You know that a graph has a perfect matching if and only if this happens. So how would you approach this? hand, I'll come and talk to you. So shall we try direct proof? Shall we try contradiction? Or shall we try something else? Any thoughts?
Makes sense to say, to try to prove that like three
Try to
regular
prove?
graph without a perfect matching is not too connected, because that seems like an easier thing to do, just find an edge which if you delete as well.
So you will take a 3 regular graph, supposing it doesn't have a perfect matching, then you will argue that the graph is not too connected. Okay? Yeah, that would be one way to do things. So, okay, let's try that. Take a 3 regular graph. Shall we assume it is connected? Yeah?
Sure.
We can take a connected 3 regular graph. Yeah? If it is not connected, then we are assuming it doesn't have a perfect match. So consider a 3 regular graph that does not have a perfect matching. Yeah? Or I could have simply said that is not matchable, so that you get used to the term. That is not matchable. Yeah? If it is not even connected, then we are done.
Yeah, because it's
Yeah, so
not-
therefore we may assume it is connected, and our goal will be to show that it's not too connected. Yeah? So the yeah. Okay, so how shall we proceed now? So this is what we want to show. So what will we do?
Like consider some subset such that when you remove.
Yeah. Right? If the graph does not have a perfect matching, then it means that there is a violating set.
Yeah.
Right.
There is a set that violates this condition. Okay? By Tutt's theorem, there exists a set S such that the number of odd components is strictly greater than the cardinality of S.
Right.
So let's draw such a thing. This is my set S, and the components with an odd number of vertices. So convention, when I want to indicate that a component has odd number of vertices, I'll put a circle, and if I want to draw a component with even number of vertices, I'll put a square. Is that okay?
Cool.
So I'm not going to draw the even ones. I'm just stating it. So these are all odd components according to my convention. So I put 5 here, so at least 6 here.
Okay.
Yeah. All right. So let me ask you, how many vertices in a 3 regular graph? Even number. You agree? You all agree? A 3 regular graph by the handshaking lemma has an even number of vertices. So if I have 6 odd components, is that possible? Could I be deleting 5 vertices and getting 6 odd components?
No.
No, right? You all agree?
Yes.
How many should I have?
Can you repeat again the statement?
At least one more. Okay.
At least 7.
Okay.
Or
that's
you could
okay.
like delete like 2 vertices and maybe get this, I don't know.
Yeah, so there should be at least 2 more, right? Do you all agree? If I delete 5 vertices,
Yeah.
I should get at least
7.
7 odd components.
Okay.
Right? Given that I am getting at least 6, there should be at least 7 by parity.
Makes sense.
Observe that parity keeps coming up.
Alright.
Parity is probably the most important thing in matching theory. Right? Nothing happens without parity. So if I delete 5, I should get at least 7. Okay, fine. Okay. So what? How do we finish the proof from here, right? So the goal is to show that the graph is not too connected. So maybe you all can try. See if you can make some progress.
Okay, I think.
Okay, so if you make some progress, just raise your hand and I'll come and talk to you. Yeah. We put this last one by parity. And as I said, parity is crucial in life. I'll come and talk to you. So here is something worth thinking about. Consider a component. Let's say this is J. What can you say about partial of the vertex set of J? Remember the notation? This means the number of edges that have one end in this component and the other end is outside this component in the graph G. Right? So think about this quantity. For each component, for each odd component, right? I've only drawn the odd components here. For each odd component, what can you say about this quantity? Yeah, if you have any thoughts, let me know.
We can say that it has to be odd. Should be one of the because 3 is not connect anything inside its own component. It has to be one. If you remove this as
If you repeat the 3 volume, so it's 1 or 3 is clear.
so it is either 1 or 3. If it's 3, then you cannot. It's not connected anything inside its own component, which is not possible.
No, I see how it's also around. I could have a triangle. 3 is just going out.
No, but then the graph is 3 regular. So all the 3 of its edges are like on that in S.
In the right. Okay, while you make a drawing, I'll just check.
Yeah, so obviously there cannot be only one vertex coming out of a component, right? One edge, sorry. Because otherwise there is like, I meant to say there is not the opposite vertex. There won't be biconnected. So at least 3, so I have at least 21 edges.
Why not 2?
That's odd, right? So we have 21 edges going to those 5 edges. That's pretty bad.
We can say that if you have 3 edges coming out like this.
Why not? Let's do also like this. No?
Okay, so if there is 1, then we cannot have that because we can disconnect that image. Okay,
Why was it odd again, the like number of...
Sorry?
Why was this odd again, the number of edges coming out from it?
I don't know. You tell me.
Oh, okay.
So out of each component there are 3 edges coming out, so n plus 2 such components. But there are only n vertices here. So if PHP component had to have more than 3 edges coming out of it. We have n plus 2 components. And by PHP model we have to have more than 3 edges.
Okay, anyone else? So to make things slightly easier to explain, I'm going to make it a proof by contradiction, but it's basically the same thing. It will just make it a bit simpler for me to explain things, but essentially the same argument can be converted into this. So what I'll do is, I'll just consider it to connect its regular graph that is not matchable, and we'll arrive at a contradiction. It will just allow me to treat components uniformly to arrive at a contradiction. Yeah. So what can you say about this quantity? Because the graph is too connected, can I say that there should be at least some number of edges coming out of here?
At least 2.
At least 2, you all agree? At least 2, everybody agrees? Okay, so this quantity is at least 2. For this we use the fact that the graph is too connected. Yeah, so for each component, let me put 2 edges coming out. And the other ends of these edges must be where? They have to be here, right? By definition of component.
Yeah. Okay.
So the other end has to be here. Okay. Can we make this at least 2 stronger? Right? If we can make this at least 2 stronger, then do you all agree that we are actually done by counting?
Yeah.
Okay. So the question is, can we make it more than at least 2? And here is where, don't forget the graph is 3 regular. Because it is not true that every 2 connected graph has a perfect matching. Every 2 connected graph need not have a perfect matching. Somewhere in the proof, you must use the 3 regularity. Right? So we have used it once in a very, very weak way, but maybe you should use it in a slightly stronger way somewhere. Right? So now can you think about, in a 3 regular graph, what can you say about this and this? Maybe not S, E. For any set of vertices, what can you say about these 2 quantities? T is a subset of the vertex set. Is there any relation between the order of T, the cardinality of T, and the cardinality of the cut corresponding to T, partial of T?
Congruent mod 2.
They are congruent mod 2,
Yeah.
right? Congruent mod 2, we have seen earlier in life today, in the context of perfect matchings. They are congruent mod 2. Yeah? So therefore, how many edges coming out of each?
At least 3.
At least 3. "21 edges coming out of here. How many going there? At most 15. 21 greater than 15 last I checked. Yeah? Okay. So we're done. Yeah?
We actually didn't need the fact that like there are 7s, not 6s.
We did not use that fact. That's a good point. I just wanted to emphasize the role of parity. Good point. We did not need this last component. 18 is already greater than 15. Yeah? Thank you. Good. So we are done. So this is the proof of Petersen's theorem. Petersen had a pretty lengthy proof that I don't want to read ever. Tut read it as a teenager, because that was Tut. Right? And then at the age of 30, Tut gave a short proof. Of course, short proof using a hammer called Tut's perfect matching theorem. But the hammer is pretty, right? The hammer is really nice.
Why do 3 regular graphs have to have an even number of vertices?
You tell me. Every vertex is degree 3. So how many vertices of degree 3?
Oh, if it's odd, then there'll be an odd total. Oh.
Yeah, handshaking them.
Okay,
Yeah.
that's.
Yeah, cool. Okay, good. Alright. So are we all done with this? Is everybody convinced that a two connected three regular graph has a perfect matching? Yeah? Okay. So we are done with this. Let's erase it. The proof. Actually the theorem is there. So erase the theorem also. Okay. So QED. So now we want to prove the next statement. A three regular graph is matching covered. So what is matching covered? It's a connected graph. Every edge belongs to some perfect matching. Yeah? We'll assume connected in definition of matching covered because in graph theory you almost always assume connected, otherwise it's annoying. There is one issue. This graph is also matching covered according to this definition. Yeah, which is very unpleasant. It doesn't even have a perfect matching. So we will say the graph has at least two vertices. Is that okay? Right? It's a connected graph, at least two vertices. Every edge belongs to some perfect matching. Yeah? And the statement is that a three regular graph is matching covered if and only if it is two connected. To become slightly familiar with matching covered graphs, let's prove a weaker statement. Every matching covered graph is two connected. Here is an easy statement. Try it yourself, DIY, for now, not for later. Every matching covered graph is two connected. We saw two definitions of two connected. One definition was that between any two vertices, there should be two internally disjoint paths. Right? There should be two internally disjoint paths. Or the graph is connected, and if I delete any vertex, then the graph is still connected. Observe that this equivalence is false for this graph. This graph is two connected as per one definition, but not two connected as per the other definition. And that is why I said in those equivalences, you generally have to deal with small graphs. So this is that fellow, K2. If you delete any vertex, the graph is still connected because K1 is connected by definition. But there are no two internally disjoint paths between these two. There is only one path, the edge. Okay. So, anyways, so this fellow is two connected or not two connected depending on your definition.
Which definition are we using here?
Right. I am going to use internally disjoint paths.
Oh.
So because of that, I am going to put except K2. Actually, wait. What is the definition I use for two connected? Internally disjoint paths. That's what it is. Yeah. And it's just annoyingly small examples. Yeah. Okay. I'm going to use internally disjoint paths. That's my standard definition. So therefore, I have to exclude K2. Okay. So can we prove this?
Yeah, one second.
Consider a graph that is not two connected.
So it has one really important edge.
Okay, just write it down. I'll comment on it. Yeah, I want everybody to have some time. So, supposing I give you a graph G that is connected but not two connected. Yeah, you're on the right track. So that what does this mean? It's connected but not two connected. Except for one and two vertices, the two definitions are equivalent. So we'll use the other one now, right? We won't use internally disjoint paths. We'll use the fact that there is a vertex you can delete and disconnect the graph. So that means that there exists a cut vertex. What is a cut vertex? It's a vertex you delete, G minus V is disconnected. So there is a vertex V and G minus V is disconnected. Now see if you can complete the proof. And raise your hand if you can. Yeah. Let's draw some components. If I delete this vertex, I get some components. One component, another component, I don't know. Maybe this is what it looks like. This is one possibility. There could be 10 components.
Yeah. So is it fine if I assume there's an edge whose removal disconnects the graph?
Not quite. No. In general, this is not true. In general, it's not true that if there is a vertex you can delete to disconnect the graph, and there's an edge you can delete. See if you can make an example.
In the case of 3 regular, that's okay, but in general, that's not okay. A hint is try to complete the proof in this case that I've drawn. If you can complete the proof in this case, you can complete it in other cases.
Are you still using a symbol of even component?
Yeah, that's right. Yeah, this is even component, this is odd component in my drawing. Of course, why should be there one of each? I don't know. Maybe there shouldn't. I don't know.
So
Yeah.
I'm not sure if it is correct. Just if there is any odd component, then the edge going from V to that odd component has to be there in everyone, which means from that other side, any of the edges you cannot include. And similarly for even from that
And you said if there is any odd component.
so the
Can
edge,
it an odd component be?
yeah, so if the one component is bigger than the edge from V to that component, you can't include that.
If all components here, how many vertices in the graph? Yeah.
Or that.
Yeah.
And a different thing about
That's not true. No. In 3 regular, no. There's a vertex you can delete to disconnect. That doesn't mean there's an edge.
Now if it's 3 or more, then we have sense that for each of these kind of each of these. So each of those, so there is a performative class that to and it's all this kind of so it is now if it's only one more company, then and this one more even comes same one might work.
Yeah. See if you can shorten it.
One second. There is no previously this is vertex matching. There is no edge between the vertex and the event. You can't have a vertex from the vertex from an edge from the vertex to the event component. So there are 2 all odd components. But at 7 there is at most 1 odd component. If there is 1 odd, there cannot be no odd components because you know that. So we are done, right? Because you know 2 odd.
Yeah. So I think most of you have the argument more or less. So yeah, does everybody kind of see how to proceed? Yeah, have you convinced yourself? Yeah. So you just look at the parities of the components, right? And note that the graph is matching covered. In particular, it's a perfect matching, right? So supposing there is an even component in G minus 3. That means that edges like this, can they be in a perfect matching?
No.
These edges cannot be in a perfect matching. Right? Is that correct? Yeah. If there is an even component, then any edge joining V to that component, having one end in V and one end in that even component, that is not in a perfect matching. So therefore, even components are not possible. You just have a bunch of odd components. Is that correct? So, yeah, something like this. But now observe that in any perfect matching, what will any perfect matching look like? Can there be a perfect matching now?
No.
Now this is a contradiction to Tutt's theorem. Right? Now there is no perfect matching. You delete the vertex V and you get two or more odd components. We already ruled out even components. The graph is disconnected, so there are two or more components. They are all odd components. Well, then there is no perfect matching. Forget matching covered. Yeah? So you're done. Okay? So we proved that every matching covered graph is two connected.
No, you need to show that this one.
Yeah?
And not.
So this is proved. Every matching covered graph is two connected. Every two connected graph is not matching covered. Yeah? You can easily make examples. Can you make an example? Can somebody construct a two connected graph? Well, of course you will tell me odd number of vertices. No, that's not all. Can you construct a two connected graph with an even number of vertices? That is not matching covered. See if you can construct a two connected graph with an even number of vertices. That is not matching covered. Two connected, even order is number of vertices,
Sir?
but not matching covered. Yeah, you can come and draw it here.
It's just K4 without an edge.
Okay. Sure, that works.
Yeah, not before.
This graph is not matching covered. Every edge except one edge belongs to a perfect matching. Right? This edge does not belong to any perfect matching.
There's
Yeah.
one addition.
Okay.
There's no fraction of
Cool.
breaks. The P of P.
Alright. So,
It's all
fine.
connected.
This is that.
I think the complete.
But now we want to prove the stronger statement. We have proved Petersen's theorem. We want to now prove that if the graph is two connected and three regular, this is the only thing that remains, right? Because we have proved matching covered implies two connected, right? That is for all graphs, so therefore it is true for three regular graphs. So the only thing that remains is to show that a two connected three regular graph
First concept is matchable, this is matching covered.
we know it as matchable. We know it is matchable. So maybe we should try to understand when is a connected matchable graph matching covered. If we can understand this, then we should be able to answer this, following the same thought that Tutt probably followed, right? So, can we characterize or understand whatever connected matchable graphs that are matching covered. In other words, I want a result that looks like this. Desired result a connected matchable graph is matching covered if and only if blah. Yeah? If we have a result like this, we should be able to just use that as a hammer to finish this off. Yeah, that would be nice. So, supposing we have a connected matchable graph that is not matching covered. What can you say? What does it mean to be not matching covered?
There is some edge.
There is some edge that does not belong to any perfect matching. Let's say G is a connected matchable graph that is not matching covered. This implies there exists an edge E, UV, with ends U and V, such that E is not in any perfect matching. Yeah?
Yeah.
An edge is not in any perfect matching. What does that really mean?
So
So keep it to yourself. I'll come and talk to you. Yeah, let's give everybody a chance to think. An edge UV not being in any perfect matching. If you have figured out an equivalent statement, write it down and I'll just come and read it, so that we don't reveal the suspense to the others. Yeah? Just write it down. An edge EUV is not in any perfect matching. What does that really mean? I don't have any theorems for an edge not being in any perfect matching. I only have results for a graph having a perfect matching or not. So, what does it mean for an edge to not be in any perfect matching? Yeah, I want something equivalent to this. Okay, anyone else? An edge not being in a perfect matching is equivalent to some other nice statement. Right, so I'm not looking for anything too technical here. I just want to write a statement that this edge not being in any perfect matching of G is the same as some graph blah does not have a perfect matching. This is what I'm looking for. The edge not being in any perfect matching, which means some graph, this is equivalent to saying that a certain graph has no perfect matching. Yeah, what is that certain graph? Right? Think about what a perfect matching containing the edge looks like. A perfect matching containing the edge looks like this, spanning one regular subgraph. So this edge not being in any perfect matching just means that this graph, where I have not drawn all the edges, does not have a perfect matching. You all agree?
Yeah.
So these two statements are equivalent. You all agree? The edge UV does not belong to a perfect matching if and only if, perfect matching of G of course, if and only if the graph G minus U minus V has no perfect matching. But this is a nice statement because we have a statement like this. Right? This is the kind of statement we want because then we can just apply the hammer called Thutt's theorem. Right? So please apply the hammer and see what happens. So what does this mean? There is a, in G minus U minus V, there is a, in that graph there is a set of vertices, let's say 5 vertices, so that when I delete those 5 vertices, I get at least how many odd components? 7. Yeah? Okay. So, in G minus U minus V, I'll just make a drawing now, because I'm running out of space. In the graph G minus U minus V, there is a situation. I delete some 5 vertices for any value of 5 you like, and I get at least 5 plus 2 odd components, once again by parity, because the original graph has an even number of vertices. It's a matchable graph, therefore it is even number. When I delete 2 vertices, I still have an even number of vertices, right? So therefore, we have a situation like this in G minus U minus V. Okay. We are making some progress in life, but you would like to say something about G, right? Okay. Add U and V to this picture. Yeah, put U and V back into this picture. So, if I put them back into the question is where should I put them? Well, I can put them wherever I like. I will put them on the top here. Right? I will include U and V. I will go back to the graph G. Okay, this is the original one was G minus U minus V, and when I include the yellow things, I'm going back to the graph G. Huh? This is interesting. Why is this interesting?
It's equal.
Oh, this is equal. 7 is equal to 7. So I was able to delete some 7 vertices, including U and V, by the way, in G, and I was able to get exactly 7 odd components. You all agree? Yeah. So I have a set for which equality holds, and that set has this edge E.
Sure.
Yeah, okay.
Yeah.
You all agree? In the graph G, there is a set of k vertices, including U and V, which are the ends of the original edge we chose, so that when we delete these k vertices, we get exactly k odd components. You all agree?
Yeah.
Okay. Yeah. Really?
Yes,
So
ma'am.
let's just do again.
Okay, then I guess it's. Wait 1 second.
And is everything if and only if? This is everything if and only if.
Some
Until
thing
now.
is connected to you.
This is if and only if. This is if and only if. Matchable graph, connected matchable graph that is not matching covered is the same as saying this, right? This is also if and only if.
Again, similar argument to like last.
We are done.
Yeah, we're done.
Yeah.
We have a theorem.
Because like.
We need to write down the statement. We are not done yet. We have done something, but we don't have a statement yet. Can you all write down a statement? Yeah, can you now write down a statement along these lines? A connected matchable graph is matching covered if and only if blah. I want you all to write down blah yourself and then just raise your hand and I'll come and talk to you. Yeah, you're not done yet. A connected matchable graph is matching covered if and only if blah.
Actually, what do you mean by statements? Can't we directly say like we don't?
Because that doesn't totally
Yeah, can you just write down something? What exactly did we prove? We proved something clearly, right? You just need to figure out what we proved. Sometimes in life you actually have proved something, you just don't know what you have proved. You just spend some hours or days or months to figure out what you proved. Then don't worry about beating a long statement. But yeah. In some sense, the sets where equality holds is playing an important role. The sets where equality holds, that seems to be playing an important role in whatever we have proved. What have we proved?
Yeah, something like if there's no connected units and some other set, you have like inequality and then we can say wait, this 21 is greater than 19.
Sorry, what is that?
21 is greater than 19. We can say, or in general, we will not have enough edges coming out of
Oh, I
the
see.
top part.
You're going to the cubic case, the three regular case. Okay.
And I also want you to think about the converse. If I have a set like this, 7 vertices, I delete them, I get 7 odd components. But there's an edge inside this. What can you say about that edge?
We don't have enough.
Huh?
We don't have enough perfect match.
There's no perfect matching containing that edge. Do you all agree? If I have a figure like this, 7 vertices I'm deleting, I'm getting 7 odd components for any value of 7 you like. But inside these 7 vertices, there is an edge. There is an edge joining 2 vertices in this. Then do you agree that this edge is actually not in any perfect matching?
Yeah, everything is in if and only if so far. So
Yeah, everything is if and only, right?
that makes
So,
sense.
so we want all such sets to not have any edges in them. You all agree? Do you know what set of vertices that has no edges? You know what that is called?
Independent.
Yes. Independent set, also stable set. Independent if you are in CS, stable if you are in math. I like stable. Right? So I use tables. Yeah. So, right, so whenever you have a set for which equality holds, it should be, whenever you have a set for which equality holds, it should be a stable set. For the graph to be matching covered. That's the statement. A connected matchable graph is matching covered if and only if for every set where equality holds, that set has to be stable. That's the statement you do. Yeah. The only problem is I don't have a word for that equality because I don't want to throw one more word at you. I'll call it a special set for now. If and only if every special set for the sake of is stable. Okay, special set means a set S of the vertex set, subset of the vertex set, such that number of odd components in G minus S is equal to the cardinality of S. Yeah, these are the special sets. All such special sets should be stable. Stable is just independent, in case you know that one. Yeah? So this is what we have proved. A connected matchable graph is matching covered if and only if every special set is stable. Yeah? Let me ask you, does every connected matchable graph have a special set? It's a trick question. Does every connected matchable graph have a special set? It's to get you familiarized with special sets. The number of odd components in G minus S should be equal to the number of vertices I deleted, the cardinality of S.
I think so.
Okay, what is that? Can you give me a special set that works for every connected matchable graph?
Just delete one.
Delete one vertex.
Yeah.
That will actually work. But there is also one smaller than that.
Delete none.
The empty set. Yeah? The empty set is special in any connected matchable graph. And every single vertex is also special. Right? I don't like the word special, but it is what it is. Yeah? Okay. Fine. Questions, concerns? All good?
Yeah.
Okay. So now, what was the whole point of this? The point was to prove this. Every two connected three regular graph is matching covered. Yeah? Can we all try this now? Can you all try it? We know that two connected three regular graphs are matchable.
Yeah.
So therefore they are connected matchable graphs. Now can you use this new hammer that we have? Yeah? Can you now use a new hammer to smash this?
Did we use two connected anywhere?
No, not in this. Here we did not use two connected.
No, I think probably for the finish we did.
Yeah, we need.
Here we
need
did not
for the
use
finish. We need
Here
for
for the
this
finish.
direction. Yeah.
You mean for the Petersen theorem? There we need two connected. Yeah, for Petersen theorem you need two connected.
I
Here
think
we
for
did
the
not
second
use.
part we also need but this result we don't need basically.
Sorry? Yeah, I just want you to use this
Yeah.
to just erase this part. So let me get rid of all this now. Yeah, we are done with all this. Let me give you a pretty special set in a two connected three regular graph. This is a nice two connected three regular graph. Nice because I like it.
Yeah, one more from each of the middle.
Oh, I
titles.
forgot this one.
Just one
Thanks.
more.
Yeah.
This is nice and big.
Right? This is a two connected three regular graph. And observe that this is a special set. Not empty, not single vertex, something more interesting. Yeah? You delete the three vertices, you get three odd components. So therefore it is special by definition. Yeah? Okay, so now try to prove this. DIY. Okay? Once you have figured it out, raise your hand. Or if you are stuck somewhere, raise your hand.
So I told you my idea, right?
Yeah.
Can you just briefly repeat it?
Alright, so for the special set, we have at most from the special set going out 3 and minus 2. We already have I'm done.
Oh, I see, because it shouldn't.
Yeah. If you are stuck, just make a drawing. Supposing it is not matching cover. So there will be a special set with some property. Now try to make progress from this drawing.
Similar ideas. If there's only one edge coming out of this, then on the corresponding vertex, we will connect all of these are going to at least 3. It means that if these are 3 functions, then at least 3 edges are coming out from this. But this can be strictly less than 3 vertices, not matching.
We can't have minus coming out. At least 3, so at least 3 times and 3 times x which is coming out. But that has to be seen as that is at least 3. There's equality. There's no x can be coming out.
Okay, anyone else? Has everybody figured it out? Yeah? Everybody got it? Yeah? Yeah? Do you all see? We have, I have 5 and 5. I have at least 3 edges coming out here from each. Therefore, I have at least 15. But this is a 3 regular graph. So I have at most 15. Well, at most 15, at least 15. These are equal numbers because I'm counting the same thing. So they better be equal to 15, both of them. But that just means that there can't be any edge here. Right? If there was an edge here, then this would go down from 15 to 13. Right? So there are multiple ways to write it. Essentially it all boils down to 15 equal to 15. Yeah? Alright, so we are done. We have used Tutt's theorem to basically finish off all of this 1934's work as well. Yeah? Schönberger answer. Yeah? Okay. Good. So, now that you have seen multiple applications of Tutt's theorem, are you interested in seeing a proof of Tutt's theorem? Yeah? Okay. So that's the goal for the next. Right? So when somebody asks me what is the application of my work, well, this is what I mean by application. What else do you want an application? So, Tutt's theorem has applications. Okay. So how do we prove Tutt's theorem?
Yeah.
As you can imagine, this won't be that easy. So what we will actually do is we will prove a more general result. Okay? We will prove something more general than Tutt's theorem. So Tutt's theorem is about perfect matchings. Yeah? So here's one way to think about Tutt's theorem and many results actually. So this actually goes a bit into subjects like complexity theory and all, which I'm not going to teach, but I'll try to keep it at an intuitive level. So I don't expect any familiarity with algorithms and complexity theory, but I still want to deliver the intuition. So let's try to take a second look at Tutt's theorem. Okay? So in theoretical computer science, people like to talk about decision problems. Okay, so I will give you a decision problem and we'll talk about this very briefly. Given a graph G, decide whether it is matchable. Okay, so think of it as follows. Think of it like a computer program. I'm sure you all have used computers. So, right. So I give you a graph as an input to the program, and the program should say, yes, the graph is a perfect matching. No, the graph doesn't have a perfect matching. Right? But of course, would you be happy if the program just told you the graph doesn't have a perfect matching, or the graph has a perfect matching, and that's it? And then there's just complete silence. Is that something that would make you happy? No, right? You would want something more. What would you want? If the program tells you, yes, there is a perfect matching, then you want to provide it. You want to get a perfect matching, right? The program should also tell you, here is the perfect matching, and I'm not lying to you. And you can go and check, yes, perfect matching.
And checking it is very
Checking
fast.
it is easy, right? Verifying that a given set of edges is a perfect matching or not is actually easy to see. Yeah? Yeah. So that's fine. Now what about if the program tells you, hey, the graph doesn't have a perfect matching, and that's it, silence. That also won't make you happy. What would you want?
Give me the subset.
Maximal matching.
Give me a set. What is that?
C order of G.
That.
Like a max matching. Right?
That's theorem.
Or like that, yeah.
Right? This would be nice. Because even if the program tells you, here is a matching of maximum size. Let's say the graph has 14 vertices. The program tells you, here is a matching of size 12. And it is maximum. Are you happy? No. Why are you not happy?
Why can't you add in the two other vertices?
Right. Because the program hasn't convinced you that this is a maximum matching. The program has just told you maximum matching matches 12 vertices instead of 14 vertices. So it's cardinality 6. Whereas a perfect matching would have cardinality 7 if I have 14 vertices. Yeah?
Okay.
You agree? So if the program just tells you this is the cardinality of a maximum matching and here is the maximum matching, you will still not be happy because the program hasn't convinced you that this is a maximum matching. Yeah? It would be better if the program actually knew Tut's theorem and told you here is a set that violates Tut's theorem, that inequality. Then you know that the graph doesn't have a perfect matching. They come in. Then you know that the graph definitely doesn't have a perfect matching, right? By the easy deduction of Tut's theorem. Yeah? You made entry at a good time. We just started the decision problem discussion. Alright, so is that right? Does that make sense? So you would want a program that actually gives you a certificate. Do you all agree that if the program gave you a set that violates this, you can check easily
Yeah.
that it violates? And now you are convinced that the graph actually doesn't have a perfect match. Yeah? Okay. So this is basically about decision problems. When a decision problem for a yes instance, what would a yes instance be? A graph that has a perfect matching.
Yeah.
Yeah? For a yes instance, there is a certificate. What is it? A perfect matching.
Yeah. Fair enough.
And now you also have a certificate for no instances.
Yeah, that's pretty cool.
It is a set that violates this inequality. So that is one way to think about Tut's theorem. It gives you a certificate for both. Right? So it gives you a certificate for the hardware problem, which is to convince that a graph doesn't have a perfect matching. Yeah? Alright. But now let's ask a more general question. Instead of just finding out whether the graph is a perfect matching or not, I want to actually find out whether a given matching is maximum or not. By maximum I mean as large as possible amongst all matchings. I have not defined matchings, I have only defined perfect matchings. Okay. So what is a matching? Anybody?
Just pairing up of edges as many
As possible.
Yeah.
Right? So let's write down the definition of perfect matching. Perfect matching definition that we wrote down earlier today. It is a subset of the edges such that for every vertex V, the intersection with its cut is equal to 1.
Yeah.
This is perfect matching. So what should I do here for matching? Instead of equal to 1, I will say at most 1. Either 0 or 1. So now I have the definition of a matching.
So what is the cut notation for that?
Yeah, so this is the set of edges in incident at a vertex.
Oh, okay.
It's basically a cut. You put B on one side, all the others on the other side. It's the edges going from B to the others. Yeah? Alright? So this is what a matching is. And now, instead of asking whether a graph has a perfect matching, what is the cardinality of a perfect matching? If n is the number of vertices, n by 2. Yeah? N by 2. Whereas now I can just ask, what is the cardinality of a maximum matching?
Yeah.
Yeah? So, and in fact I can pose a decision problem as follows. So, I will change the original decision problem. Given a graph G and a matching M, decide whether M is a maximum matching. Right? So let's think about this problem. If the matching is not maximum, can you convince me easily that it is not maximum? What would you show me?
A better
A
match.
better one. You would show me a better matching. Yeah, you all agree? If a matching is not maximum, you will simply show me a matching that is larger than the given matching, and I will be like, okay, fine. I will check it quickly that it is a matching. It is larger than the one I gave you. Therefore, you are not lying. And what about the others? If the matching is actually maximum, then what would you show me? Of course, if it is a perfect matching, then I don't even need to ask you anything because I know it is maximum.
Yeah.
Right? So it is interesting. This question is interesting when the graph doesn't have a perfect matching.
Yeah.
You all agree? The graph doesn't have a perfect matching. Let's say the graph has 14 vertices, and I give you a matching of cardinality 5, which means it matches 10 vertices. The remaining 4 vertices are not matched.
Yeah.
Yeah? Now I am asking you whether this is maximum. So what would you show me?
I guess it could be a set S so that C is a word of S is against cardinality of S plus 4.
That would be nice. That would be fantastic. So what he's saying is it would be great if supposing, so let's do an example. So just to write it down. Supposing the graph has 14 vertices and I give you a matching with 5 edges. That means that it matches 10 vertices.
Yeah.
So the number of unmatched vertices is equal to 4. You all agree? So what he's saying is if there were a set of k vertices, k equal to 5, for example, such that when I delete them, I get, okay, maybe my example is 14 vertices. Okay, let me put 4 vertices here, or just 3, doesn't matter. Supposing there was a set of 3 vertices, so that when I delete these 3, how many odd components? 3 plus 4, 7. Yeah? Supposing this were the situation, I delete k vertices and I get k plus 4 odd components.
Okay.
If this happens, then he is claiming that this is actually a maximum matching. Is that what you're saying?
Yeah.
Let's think about this. If the program were able to tell you that, hey, here is a set of 3 vertices, you delete and you get at least 3 plus 4, the 4 is coming from here, odd components, then it actually proves that this is a maximum matching.
Yeah.
Because in any matching, either I will match all the vertices in an odd component, in which case I will have to use one fellow from here, or I will get at least one vertex in this set that is not matched.
Okay, yeah.
You all agree? Yeah? Does that make sense? Okay. Let's write down a formal statement.
This assuming tax theorem, right?
No, we are not assuming. This is wishful thinking. This is just wishful thinking.
Wait, so we have one direction. Can you prove the other direction as well?
Oh yeah. We are going towards that. So yeah. Yeah, we are going to go there. This is actually the generalization of Tutt's theorem that we will prove. Yeah? Okay. So, but let's write down things. Let's write down things so that we know where we are heading and what we have thus far. So, what we have proved is the following. What we have observed is the following. G is a graph. S is some subset of vertices. And let's say the number of then what can we say about the number of unmatched vertices in any maximum matching? The number of unmatched vertices observe that we once again change the viewpoint. Rather than think about the cardinality of the matching, we have conveniently started thinking about the number of unmatched vertices. Yeah? The number of unmatched vertices is at least a certain quantity. What is that quantity? For any set, I can make this claim. For any subset of the vertices, I can give you a lower bound. The lower bound may be completely useless because it could actually be a negative number. That's okay. That's okay.
Oh, okay.
The lower bound could be useless. It's okay for a particular set. Yeah.
If the null set is negative.
Yeah. Null set also will allow. Will allow any set.
Yeah, but if the take null set is only negative, so it's stupid.
It might be negative. It may not be negative.
It'll be not
Depending on the number of vertices.
not
in the graph.
positive. No.
Zero. It could be zero. Yeah.
Not
Yeah. It
positive.
won't be positive. That's right. Yeah. Good. Yeah. Okay. So what is the right hand side? What should I write in the right hand side? Cardinality of?
S minus C out of G minus S.
You want to think about it again?
C out of G minus S minus.
The negative of what you said. C odd, the number of odd components of G minus S minus the cardinality of S.
Oh.
Yeah? You are agree? Yeah? Yeah? This is the quantity. Right? So this is a statement about any set of vertices. And maybe I should put a matching because what does it mean to say unmatched vertices? M is any matching. Then the number of unmatched vertices is this. Yeah? Okay. Let's write down. What does this mean? This means that whenever I have such an inequality, blah is greater than or equal to blah. I'm interested in, what am I interested in? I'm interested in minimizing this number or maximizing the number of unmatched vertices. Minimizing. I'm interested in minimizing this fellow. Yeah? Okay. But before we do that, let's also relate. So n is number of vertices. I will always use n for number of vertices. M is the cardinality of the matching, of course. We know M is matching. And U is the set of unmatched vertices. Unmatched vertices means those that give me 0. Those that give me 0, that is the set U. Is that clear? U is the set of unmatched, maybe I'll use a word, M exposed. Vertices. So, given a matching M, the exposed vertices are the ones which give you 0. These are called M exposed. And these are called M saturated. Let's do a quick example. Consider this matching, that is not a perfect matching. What are the exposed vertices? 2 and 3. The rest are saturated. Yeah? Okay. So U is a set of M exposed vertices. Can you tell me a relation between these three? N, cardinality of M, and cardinality of U. Is there a relation between these three? If you have figured it out, just write it down in your notebook and I'll come and talk to you. Yeah, let's give everybody some time to process. Yeah. Yeah.
The number of vertices is the number of vertices of the matching. The number of vertices is not part of the matching.
I think the number of edges. I saw it in this one.
So my goal in the next 10 minutes is to tell you the generalization of Tutt's theorem, right? And then in the last session we'll prove Tutt's theorem or the generalization. Yeah, anybody else figured out the relation between these three? Yeah? Yeah? Okay, cool. Yeah, anybody else wants to discuss? Figured out? Yeah? Yeah, okay, cool. Alright. Alright, fine. So we're done. Clearly, n is 2 times the cardinality of the maximum matching, or the matching under consideration. Doesn't matter if it's maximum or not. This, right? Yeah? Okay. So that means that now what can we write? Can we write something here? Can we write, instead of the unmatched vertices, this is basically the cardinality of U that we had earlier. Can we now write something in terms of m? How large is m? If you get a lower bound on the number of unmatched vertices, you get an upper bound on the cardinality of the matching. You all agree? So can you write down that inequality? See if you can convert this into an inequality for this fellow. I don't want you to be in the picture anymore. I just want n and odd components and cardinality of s. Yeah? Yeah. Is it at least? Yeah. Yeah, be careful about inequalities. They can be annoying. Yeah. Right. Now just move everything else to the other side. Keep m on the left side. Yeah, just do that part. Yeah, works. Yeah.
Like something like this.
Yeah. Yeah. You need some factor. There should be a factor somewhere. Divide by 2 or something.
Alright.
Yeah. Yeah. Make sure you have that factor. There will be an annoying divide by 2 factor somewhere. Yeah. Yeah.
Half.
Yeah. Yeah.
Just half of this.
Yeah. Hmm?
Okay.
Yeah. Yeah. Right? So everybody got this? Is it almost half of n minus this quantity, and when you do that, you will get a plus here. You all agree? Is that what you got?
Sure, sir.
Yeah.
Yeah? I tend to make a lot of arithmetic mistakes. Please check my work carefully. Yeah? Okay? Cool. Alright, so do you all agree? For any matching and for any subset of the vertex set, you have this inequality. Yeah? Therefore, I can maximize the LHS and minimize the RHS, and the inequality still holds, right? You all agree?
Yeah.
Yeah? Okay, let's write that down. So, therefore, for any graph G, if I maximize the RHS, so now I'm taking the maximum over all matchings. This is less than equal to the minimum of this quantity over all sets.
Okay.
You all agree?
So is this the theorem?
Well, less than equal to we proved it, right? This we proved. You all agree? This we have proved. Yeah? We have proved this. So, what do you think is the theorem?
Equal to like maybe
Equality holds.
For some,
maybe we like floor it or something. I don't know.
Nothing. No.
for some set.
Not, equality holds.
Oh wow.
That's
Oh yeah, because it depends on X.
Yeah. The set version is there exists a matching and a set for which equality holds.
Oh.
Right? But yes. In general, if you maximize and minimize, equality holds. That is the Tutte-Berge formula.
That's the best for me.
Yeah, Berge, already know. So, so we just proved the less than equal to the Tutte-Berge formula, or if you like, you can just call it the Tutte-Berge theorem. Yeah, it's a French name. It's supposed to be Berge, but of course I don't always pronounce names correctly. But yeah, Berge got lucky, Petersen got unlucky. Yeah. So this is the theorem. For any graph, if you maximize the left hand side and minimize the right hand side, you have equality. So now, we will say that the sets that attain equality, we will call them barriers. Right? So we will say the set is a barrier if it attains equality. A set of vertices is a barrier if it attains equality in this equation. And now those special sets, remember special sets? They're exactly barriers. That's why I did not want to use the word barrier at that time. Okay, so for a matchable graph, barrier turns out to be exactly the equality case.
Yeah.
So that's a small DIY. So I'll just write down definition. A barrier of a graph B is any subset of vertices such that this quantity is equal to the cardinality of the maximum matching, such that n minus c odd of g minus s plus cardinality of s divided by 2 is exactly equal to the cardinality of m, where m is any maximum matching.
That is for the perfect matching. Okay, got it. Okay. Got it.
Yeah. If I have any set of vertices, that basically the way to think about this, I really dislike this expression. I cannot tell you how much I dislike it. Right? The way to think about it, it is a set of vertices that actually tells you the cardinality of a maximum matching. For example, if my drawing looks like this, let's draw the example you had earlier: 3 vertices and 7 odd components. For this to be a barrier, it means that in any maximum matching of this graph, I will have 7 minus 3, 4 exposed vertices. And there is a maximum matching for which there are exactly 4 exposed vertices.
Okay.
That is what it means for this to be a barrier. Right? It actually tells you that it gives you a clear idea about the cardinality of a maximum matching. But it's easier to just look at the number of exposed vertices and then do the math that we did earlier to figure out the cardinality of maximum matching. Right? So that barrier basically tells you you will have these many exposed vertices. Right? That's it. In a maximum matching. Yeah? So that's the way to think about a barrier, not get lost in this in an equation. Right? Okay. And now the Tutte-Berge theorem just says every graph has a barrier. That's a Tutte-Berge theorem.
Okay.
By the way we have defined barrier, the theorem is just that every graph has a barrier. And this can be thought of, go back to the decision problem. Now if I give you a matching and you want to convince me that it is a maximum matching, what you will give me is a barrier. You will give me a barrier and now I am convinced that it is actually a maximum matching. Right? Yeah. And we will take a break, 3:30. For the break, of course, I have homework. What you can do is you can assume the Tutte-Berge theorem and convince yourself that Tutte's theorem is a consequence. It is just a bunch of thinking. There's not much. There's nothing deep going on here. Tutte-Berge theorem immediately gives you Tutte's theorem as a consequence. Yeah.
Mod m is the number of edges in the matching, right?
Sorry?
Mod m is the number of edges.
That's
in the
right. Cardinality of the matching. Yeah. It's the number of edges. Yeah. So that's the DIY for the break. Prove that Tutte-Berge theorem implies Tutte's theorem. So once you have proved that, hopefully you are excited to see a proof of Tutte-Berge theorem. Yeah. All right. Let's break for a break.
When was this proven?
Yeah,
by the
go
way?
ahead.
When was this proven by the way?
Tutte-Berge theorem. So I think so Tutte's theorem is 1947.
Yeah.
But after Tutte's theorem was proved, there was a flurry of activity,
Okay.
and I think I think it's in the 1950s that the Tutte-Berge theorem was proved. Yeah. Thank you.